e-learning is on combined meshing techniques in ANSYS Workbench. My name is Eric Stamper, and I'll be going over today's presentation. So just before we get going, just a quick introduction and who we are. CAE Associates, we're an engineering consulting firm specializing in FEA and CFD analyses. And we've been a channel partner of ANSYS for the past 30 years. So we provide technical support, training, and also sales of the ANSYS software. And this e-learning, it's one of many of our e-learnings that we have in the series. If you want to look at any of the past recordings that we have, those are on our web page. They're also on our YouTube channel. So this one's being recorded and it will be posted. You can find it on our web page afterwards. If you are a New York or New Jersey resident and you want to earn continuing education credits for attending this e-learning, you just need to attend the full webinar and complete the survey at the end of the presentation. And also on our webpage, we have a resource library where we put, there's a lot of information up there, different presentations, case studies, and things like that. There's a bunch of macros and scripts related to ANSYS on there, so you can always check that out. We have a bunch of things that hopefully would be relevant to different things that you're doing. And every week we update our blog, so you can check that out online as well, where each individual posts some engineering-related topic on there. And this e-learning can be found on our calendar, but we also offer training in our office. And starting this year, we're offering some online training as well. So you can find that on our calendar that's on our webpage, or you can contact us if you're interested in any training. And this e-learning, it's going to cover handling mixtures of beams, shells, and solids, and more specifically related to shared topology or forming a continuous mesh between those different mixtures of topology. So we've had a previous e-learning on combined meshing as well, but that one focused more on connecting up different element types, beams and shells and solids through contact or connections, or I should say specifically joints. So you can already check that one out. That one has already been recorded. So between these two, that should cover most of the different things related to combining mixtures of beam, shells, and solids together. We also have a 2-day meshing class that we're offering in our office, and that covers pretty much everything that's available meshing related in mechanical. And there's also a shorter version, a 4-hour online training class for meshing as well. So if you're interested in those, check us out online or contact us. Now, today's e-learning, forming conformal meshes between different types of topology. So if we look at what options we have currently, and this is related to shared topology, so the slide right here is shared topology, forming parts in design modeler or space claim. So you get a continuous mesh by, setting up the CAD that way. So solid, shell-to-shell, beam-to-beam, that's all been supported for a long time. That works pretty well with shared topology. It's just these other options where you're trying to combine solid to shell or solid to beam that can be a little more difficult. And there hasn't been a way to do that until 16. We'll talk about that. And then if you're combining shells and beams, that can be handled directly with shared topology, but there's also some other options for connecting up different types of topology not using shared topology. Those are mesh connections and things like that, which we'll talk about. So we just focus on shell beam for a second to talk about all the possible ways you could connect up and join a continuous mesh. So the first option you have is the one that probably most of us use, and that's just using shared topology in design modeler or space claim, where you have some surface or line bodies that you want to form a continuous mesh between them. In design modeler, just select those, right-click, form a new part, and then any of the surfaces or lines that are in there are going to get a conformal mesh once it goes into mechanical. And like I said, this is available in space claim too, where on the component, the properties, you can set shared topology. So that's easy common option. And then the CAD gets stuck together. The option 2 will say if you don't use a formed part, so then all the bodies, when they come into mechanical, will get meshed independent of each other. You can use a mesh connection to connect them up. So you could have gaps between the surfaces or, talk about beams and shells and things, but bodies are not meshed together, and you're going to project either the vertex or edge from a slave geometry onto the master, and in doing that, then it will close the gap or share the nodal connectivity between these two parts. So the options that we have are, we're going to connect faces. Those are going to be the master to any of the edges or vertices on a slave. That's a mesh connection. So just showing this option, you could have one line body on the left side here. It's in close proximity to the edge of this shell that's through here, and then also you got a couple shells that are close to touching too. But these are all meshed independent of each other. These red arrows show the nodes on the surface. The black arrows show the nodes on the line body. And, they don't match up. But if you use a mesh connection, then, and this can be done in an automated way too, where these get all generated. But then it will connect the mesh. So now we have coincident nodes between the beams and the shell here. So then that all lines up. And it lines up on the surfaces as well. So that's what a mesh connection is. There's another option that you can use to connect, we're talking about beams and shells at the moment, where you can use a node merge. And then it's new in 16. So you have a line body on the left, again, same exact geometry. But in this case, we are meshing the line body and the surface edge in a way that we have nodes that are nearly coincident to each other, and also the same count, number of nodes. So if you use a node merge, then it just simply merges the nodes within a certain tolerance. So this is a little bit more difficult to set up, because if you had, on the left here, if this was one line body and it wasn't broken up into individual edges, you'd have to have, make this mesh line up in some way that you could merge the nodes together. If you break the edge on the line body here, you can easily make the mesh match up between those two edges. But this will connect up different topologies with a node merge. So those are the three different ways we can connect up different types of topologies. Now, if we just start off here with forming a conformal mesh with just a bunch of line bodies. And line bodies, they can come from Design Modeler, they can come from Space Claim, but wherever you have them, if you want to have all of the line bodies share a continuous mesh, I recommend that you just do this with shared topology in the CAD system. So that tends to be a little bit more robust as opposed to trying to bring over all the line bodies not formed into a part into mechanical and then use a pinch or some other way to connect them together. This just seems to work a little easier. And one of the nice things about Space Claim, too, is that if you have the line bodies, if you have solids that represent the beams, there's a utility in there to extract the beam cross-section of the solid and then also pull out what the cross-sectional properties are and the orientation of them and apply those to all the line bodies. So that's a nice feature that's in Space Claim that's not in Design Modeler. So that's one way to connect up line bodies. Connecting up surfaces so you can get a continuous mesh. This is something that's always commonly an issue, is that you have a bunch of surfaces. These could be generated from a mid-surface operation or just created from the CAD system, and then they're not matched up perfect where if you did form a part in Design Modeler, that the nodes and elements wouldn't get connected in mechanical just because there's gaps in the surfaces. So Design Modeler has an automated way to extend all the surfaces and then form joints or basically connections between all those different surfaces. Space Claim has the same exact capability as well. But in doing this, a lot of times the tolerances just need to be pretty tight on the CAD side in order for get this mesh to line up. So a lot of times you're not going to get the nodes and elements to be connecting the two surfaces together. So in mechanical, you can use a mesh connection, afterwards to, basically tie these surfaces together. So if we zoomed in on this one geometry here, we'd see that, we have some edges that didn't get projected up and connected in here. And maybe just, because of the tolerances. Well, if we don't want to worry about this too much to fix on the CAD side, import this geometry as it is into mechanical and use a mesh connection in an automated way, and then you can project all these, or basically just connect the mesh up at one line of nodes along this surface. And you see that the elements kind of kink over a little bit too. You got to do something, right? Because you're changing the geometry at this point. You're just kind of connecting it all together. So if you didn't want this, there is an option that you could just have this be projected straight to this surface and leave the small little surfaces in there that would be a result of the projection, but this would result in a coarser mesh. So just showing one way you can connect these things up with a mesh connection. Another situation you might have is with a bunch of surfaces too. Surfaces could be this, large and then not divided up. So this yellow surface goes through a whole bunch of other surfaces, and you got these other surfaces that aren't broken up. So there's an intersection here between these surfaces. There's no line that gets formed. So the mesh would not be connected between these two bodies. So in Design Modeler, you can form these into a part. If you do that, then when it comes into mechanical, it will create the edge that's in there. So it will slice up the surfaces, to form this connection in there. So that's nice. So if you brought that geometry into mechanical, with shared topology and Design Modeler, and you'd get this mesh that's shown here where it's connected, and you get a yellow line here. If you color by connection, you can see all the free edges. So if you went through and then checked that, this matches up, but all the edges down here in the bottom are in red. Those didn't get connected. So we need a way to clean this up without having to go back to the CAD system. We could use a mesh connection to fix this. So mesh connections, you can just right-click on mesh in the outline, and then we'll see the mesh connection group show up. This is in version 16. In version 15, you had mesh connections as well, but those showed up under the connections branch in the outline tree. So these have been moved to a new location. But in any case, you insert it, so you get a mesh connection group under mesh edit in the tree, and you just scope it to a bunch of the bodies that you want to connect together, and then you give it a tolerance to search for. So if you right-click on mesh connection group, detect connections, it will form all the connections. And if you generate those, then it will perform the mesh connection step. So notice in the process here, we have a completed mesh. So this was mesh, and it was all set with the green check mark. When we insert the mesh connections, those happen post-mesh. So, it takes this existing mesh and then modifies it to connect it up. And when we, evaluate all these mesh connections, then we see that we got some triple edges down here. So this mesh is now connected down the bottom. So that's the way that works. You can also view these different mesh connections on the geometry. If you went up, the outline tree, click geometry. You can use this, this edge coloring for the geometry as well, and then you would see the CAD showing those connections. So, those are some things you can do with surfaces, but that can also be used with combining beams and shells. So if we look at that for a moment, and let's say we had this example where we look at the part that's up on the very top right to start off with. So we have two surfaces in here. One is green, one is gray, and each of these surfaces have 4 edges on them, and all of the edges have a line body that's coincident with those. So in this case, if you were to form a part in Design Modeler with this geometry and solve this problem with some loading and mechanical, everything would look good. We would all be connected up with a continuous mesh, and there wouldn't be any problems there. That's because in this case, shared topology in Design Modeler is going to merge the vertices between the shells and the beams in there. So as long as you have a vertice at all these points and a beam at all those, they'll all get connected up. Now, if you look at this part to the left here, the surface now extends from the 4 corners of, or basically this one green surface is the whole thing. So we got 4 vertices that are shared at the beam and surface locations. So those get merged. We see that those are connected up on these edges, but there was not a vertice on this one edge of the surface body, so that didn't get merged together. So we see that that's not connected at that location. So we could go back and put a vertice there, but basically from just doing nothing else in Design Modeler, that's not going to be connected. So the way that you would do this in Design Modeler is to create a joint. And the joint's between the surface and line bodies, and then it will get connected right here and take care of this for us. So just one extra step, not a really big deal. And if you really wanted to, you didn't even have to go back to Design Modeler to do this. In mechanical, you could use a mesh connection. and connect these edges to this surface. And then you'd also get the same result in there. But just realize that the mesh connections, as we said, it's a master face to a vertex or edge that gets projected onto it. So it's not taking this one vertex here and it's not connecting it to this edge right here. It's not doing connections like that. You're grabbing the edge to the face. But anyway, it joins it up the way that we'd want. So, performing these steps, you would go into Design Modeler, you would insert a joint, and then you would scope that to all the surfaces and all the lines. So if we look at this 10th example, just select all of that geometry, create a joint from that, and then we form shared topology. So we have a surface and a line body and a part, and then the details of that is shared topology method edge joint. So anywhere that there's an edge joint, it's going to form a continuous mesh between these two topologies. So then, what you could do, just another example, is if you had a surface and a line body in Design Modeler, and you created a joint, but you create the joint on only one edge of a line body. This part right here it's a one shell, and then there's one line body that goes from each end here. But the line body has two edges, so you can see that this is the cross-section turned on for the beam. So there's two edges to the beam. So we created a joint from the one edge of the line body to this face of the shell here. And when we do that, we then form a new part, shared topology. And if you want to do in Design Modeler, you can view the edge connections, and then it turns this edge blue. So that means that we have an edge joint there, it's in shared topology, and there's going to be a continuous mesh at this location. Before we form the part, but we had the joint in there, no shared topology, it's red. So you can verify in Design Modeler that you're going to get a continuous mesh. So then we import this into mechanical, and we see that for that one edge, we do get a continuous mesh, and then it's not connected. The beam and shell are not connected over here because it's not formed. There's no joint there in the shared topology. So then a case that a joint and shared topology is not going to help you in Design Modeler when you want to form a continuous mesh is the endpoint of a beam to a surface. Or we may want this node on the surface to be connected up to the beam. So one thing you can do is in mechanical, you can use a mesh control called pinch, and you can pinch all of these vertices to the face. And if you do that, that will form a continuous mesh between these different line bodies and surfaces. And if you really wanted to, you could project that vertice in Design Modeler onto this surface and then create a vertex on that face. And then if you form shared topology, it'll merge the vertices, so then you'd end up getting shared topology in here. But if you didn't want to have to do that step, you could just go into mechanical and pinch it together. Now, if we wanted to connect up the same geometry with a mesh connection, we can do that as well. So if we wanted to grab these vertices and then connect them to this face, we can do that with a mesh connection. And actually, the mesh connection, you can see, is doing the same exact thing as a pinch that I just talked about. Right here is a pinch. If you have a pinch in version 15, when you import that model into 16 or open it into 16, these pinches get converted over into mesh connections automatically. So this is sort of the way that the things are headed, is to use mesh connections to connect up the different topologies. So this is one way you can connect up vertices to a face. The other option we said was that we can connect edges to faces. So the edges could also pass through a face, like what's shown here. So in this case, those nodes will get connected between the beams and the surface in this manner. And then the edges could also be parallel or coincident with the surface too. So an edge could just randomly go through a surface, and it'll get connected in this way. So one of the things I want to point out, though, is that all of these cases we've been talking about are for connecting lines and surface bodies with the mesh connection. You cannot use an edge on a solid or vertice on a solid or face on a solid. You can't use any of those options in what's shown here. Faces, edges, vertices all have to be a combination of the line or surface bodies. So it won't work for solids. just showing you an example of how you can go about connecting up beams and shells. So we have this geometry here, which is made up of a whole bunch of beams and shells. And it's already meshed in here. And then what we want to do is, if we have a beam and shell model, we want to turn on edge coloring by connection. So we can see here now that all of these red single edges are not connected up in any way. And we can we can clearly see that the mesh does not line up either. So we want to connect these up. Do that by right-clicking on Mesh, Insert, Mesh Connection Group. So in here, I'm going to say all bodies to be connected, and just give it a tolerance that it's going to look for. So we could have gaps between these different surfaces, as long as they're within this tolerance, the size of the circle that's shown here. Then we right-click and detect the connections. We get all these different connections that got created. So we can go through these and then see what's going to get connected together. So this one right here is this face shown in red is going to get connected to all of these edges in blue in here. And you could look at all of those. It's going to right-click and connect the mesh. And then go back here and view the mesh, and now we see that the edges get a different color, indicating that they've been connected up, and we can also see that the elements are connected through here. You can zoom in and look at all these different locations and see that the mesh was connected up on everything in here. So that works very quickly. If you have large assemblies, sometimes this can be to your advantage by having all the parts not formed into a part, because then you can take advantage of the multiple CPU meshing, so each body can get sent off to a different core. So you can potentially see some speed improvements in overall mesh time doing this versus trying to form shared topology in Design Modeler. So it's as simple as that to make some mesh connections. Now, what happens when we want to deal with solids and use some shared topology between solids or shells? Start off with solid and shell. So you can, go in there in Design Modeler and group a solid and a surface body together and form it into a part. If you do that, though, you're not going to get both of these topologies to import into mechanical and get a shared mesh. What you will get is this one body is going to get intersected by this surface body, and it's going to get split up. So now we have a whole bunch of bodies that get formed when this gets brought into mechanical. The surface that we have here does not get imported into mechanical. And all these bodies here, since they're formed into a part, these split bodies will get a continuous mesh formed between them. So that's the end result of doing this. And I use this, once in a while too. I'll create some surfaces and then split the geometry this way. Sometimes that can be a little faster. So that's what you're going to get. Now, what you cannot do, though, is if you try to form a part between a surface body and a line body, you're just going to get an error. You can't do that. So solid and line body shared topology is not supported in Design Modeler. So then, what options are we left with if we want to connect a surface body or a line body to a solid? So what we're left with is the node merge option, which is available in 16. And we can merge any of the topologies together. They can be lines, surfaces, solids, any combination of that. And the node merge works for vertex to vertex, and then any of the combinations you could have up to face to face. So it could be a face on a surface or a solid, or a vertex on a line and solid. Any of the combinations, any of the topologies, you can merge them together. So the example that I have shown here on the right is that it's a gray cube, so mesh with solid elements. We have a surface body up on the top and brown, and then a bunch of line bodies on the bottom. These are all meshed independent of each other, but the meshes were created in a way that the nodes are very close to being coincident with each other between the different topologies. So the node merge will merge all this together. So one of the difficult things that you might see if you try to use this is that you need to make the mesh pattern match up between let's say the surface body, for instance, and the solid. And that isn't always the easiest thing to do. What I did is I imprinted the solid onto the face of the surface, so you see that that geometry does look the same between both, and then I could put on consistent mesh controls to get the nodes to line up in there. That might be difficult to do for more complicated parts, but if you can get that to line up, then you can use the node merge, and then it will get connected together. So then when you go about solving a problem like this, you can see the beams and the shell and all this is connected up at the mesh level. So that's, I guess, the other point here is, too, if you do the node merge, you want to make sure that the nodes are close to being coincident. If you use a large tolerance and you have a different number of nodes on each, you could make some poorly shaped elements. So that's really it for all of the different options that we have for connecting up the different topologies to get a continuous mesh in mechanical. So I do thank everyone for attending